Hello all. So now let's discuss our second modulation scheme, that is PSK, or we can say phase shift keying. So in the most general form, the M signal waveforms, again as we started with for ASK, the M signal waveforms are represented as follows, that is SM of T. Now as we already know from the name that our information will be passing in the form of phase changes, right? Not in the form of amplitudes. So I'm directly writing the passband signal right now. No, I'm not going into baseband. This we already know that the real part of e power j 2 pi m minus 1. Just bear with me. I'll explain this. What is this? So this is our signal, which is nothing but our baseband signal, right? And we already know if we multiply our baseband signal with a rotating complex exponential, that is e power 2 pi fct, and we will take real part of it, then we will get our passband. So it is our passband signal, phase modulated passband signal, or PSK signal. So I can write it as g of t into cosine of, the argument will be cos 2 pi fct. We know argument will be added if they are an exponent. So just I am adding this thing, and again I forgot to mention m will range from 1 to capital M. The small m will range from 1 to capital M. So as you can see, this is the argument of cosine, and this is our Sm of t, which is nothing but our phase modulated signal. So just compare this thing how we started for ASK. Okay, in ASK we started with AM into P of t, and then in most generic form we can write P of t as G of t into cosine, right? So again we started with this g of t into some exponential, because we know that for different values of m we will get different phases here, and thus it satisfy our modulation scheme name, that phase shift keying, that is our information is transmitted in the form of difference in phases, right? So we'll see this when we plot the constellation of the same. So just follow this. So this is our the representation of PSK signal in passband, and we know what is G of t. G of t is here the signal pulse, okay, or pulse shaping filter that we have in our digital communication system. And theta of m here, theta with argument small m, is given by this 2 pi by capital M into m minus 1, this thing. So for different values of m we will have different thetas, and thus different phases. So here it will be m possible different phases, so we will have m different phases, different phases. Now let's try to calculate again the energy. Then again we will follow our simple procedure. We will find for baseband as well as passband. So here, since everything is depending on the phase and thus nothing is in the amplitude, right? So energy will be the same. So average energy is given by just Em, right? And which is nothing but, in passband it will be Eg by 2. So let me differentiate that this is in baseband and this is in passband. Mind it. So continuing with our passband, so average bit energy will be, we already know, the Eg by 2 into log m to the base 2. That's it, right? Now let's try to find phi 1 and phi 2 that we did for ASK as well. So in ASK it was just phi of t because that was one dimension, but here we will see that how we get 2D case. Okay, so for that again let me go to the previous page, and you can see that this term cosine into this, right, can be written as cos A cos B minus sin A sin B. We know the formula for cosine. So I'm taking this the new page, and I'm writing that my Sm of t can be written as g of t is outside as it is. I'm just writing cos A. So this is cosine A, then cosine of B, which is nothing but 2 pi fct. We have two arguments A and B. This is A and this is B, minus g of t is there and sin A sin B. I have just given g of t to both the terms, or you can take it outside as a common term. So this is sine first argument and sine second argument b, right? Now if you can observe that this g of t into cos 2 pi fct and this g of t into sine 2 pi fct are orthogonal, because we know that cosine and sine both are orthogonal. So, and if they are multiplied with the same factor g of t and g of t, then also they will be orthogonal, right? And what we want is orthonormal basis functions, and we know that orthonormal basis functions are orthogonal, right? Just we have to now normalize them to unit energy. So our first orthonormal function will be under root 2 by eg g of t cos 2 pi fct, right? So basically we know that energy of g of t is eg, so I'm just dividing it by root eg, and we know cosine energy is we are getting 2, so I'm just 1 by 2, so I'm just multiplying with 2, okay, and under root, because we are writing not energy but the signal. And the similar thing, if you don't get above equation, you will get it from here, that phi 2 is given as, I'm taking minus sign as well, okay, minus g of t into sine 2 pi fct, and we are just dividing 2 by eg, right? Or you can take minus sign just outside. So again g of t dividing by its energy, and we know sine is also having energy because sine square can be written as the same thing, right? So 1 minus cos theta by 2, so we will get 2 here, right? So we have our two orthonormal basis functions. Now they are orthonormal, right? Previously these were just orthogonal, we normalize them, okay? So now the energy of this will be 1, and we are having now just our ortho normal basis. Now we can write Sm of t in terms of phi 1 and phi 2, the same thing that we did for ASK, right? So I am doing nothing new. So Sm of t can be written as under root Eg by 2 cosine 2 pi by m into m minus 1, and we are having phi 1 of t. So as you can see here, that this thing I just wrote in terms of phi 1 of t, and we know phi 1 of t is having 1 this scaling parameter 2 by eg, and in order to compensate that we are having eg by 2, okay? And the similar thing, plus sign will be there because we already considered minus sign in our phi 2t. So mind it, sine 2 pi by m into m minus 1, and it will be phi 2 of t, right? So as you can see, we have 2d case now, right? Previously it was just 1d case, but now it will be a 2d case, right? So I'm plotting first for m equals to 2, then for m equals to 4, okay? So let me plot. So you can see this is our phi 1 of t, our basis, and this is our phi 2 of t in 2d case. And you can see for m equals to 2 it will be 1d case, right? Because this second term will be 0, right? Sine. So we will just get here 1 and here 0, right? So how, just if we won't write phi 1 and phi 2, we can write the coordinates like just Sm, which is nothing but Eg by 2 cos 2 pi by m into m minus 1. It is our first coordinate, that is corresponding to phi 1t, and the second coordinate, so we can write it like this, comma, and the second coordinate sine 2 pi by m into m minus 1. Now for m equals to 2 case, it will be, you can see that from here or here, let me change the color and show you that from here, if m equals to 2, you can see it will be pi, right? And there will be two different symbols, that first for m equals to 1, because we know m will range from, sorry, the m will range from 1 to capital M. Since m is 2, m is just 1 and 2 in here for the very first case. So for m is 1, we are having 0, and we know cos 0 is 1, right? So we are having first coordinate as 1, and the second will be, you can see here, we are getting pi, and we know anything multiplied by pi will be 0 only. And here also for m equals to 1 it will be 0, so sine 0 is 0, so we are getting 1 comma 0, which is here, right? 1 comma 0. So the first symbol is here, which is 1 comma 0, which is our binary bit 1, okay? Don't confuse with this 1 and 1, this is binary bit 1, this is binary bit 0. And similarly for m equals to 1, m equals to 2, you will get the second will be minus 1 comma 0. So in m equals to 2 case, we are just getting two things, which is also called VPSK. And if you can notice, this is nothing but binary phase shift keying. We are having just two symbols, bit 0 and bit 1, which is same as PEM. You can see this, same as PEM for m equals to 2 case, right? Now let's consider four symbols, that is, this will be called QPSK. Okay, so it will be just the quadrature phase shift keying. So since we are having four symbols, so it will be 0 0 0 1, again we will follow gray coding, and 1 0. So here 1 1 and here 1 0, not the other way around. So for m equals to 4, if you will see, you will get, right, for first symbol you will get 2 points here, then for second, then for third, and then for fourth. For all the 4 points you will get 4 different points, 1 comma 0, 0 comma 1, then minus 1 comma 0, and 0 comma minus 1, right? So since you can see, it is a 2D case, right? So it is very simple, right? And you can similarly extend for octal PSK, that is for 8 symbols. So you can see for m equals to 4, we have 4 different phases: 0 degrees, 90 degrees, 180 degrees, and 270 degrees, right? For m equals to 2, just 2 phases: 0 degrees and minus 180 degrees, right? Or 180 degrees, right? So now let's again calculate the Euclidean distance between any 2 points. So we know our point SM, so let's take 2 points SM and SN, and let's calculate its Euclidean distance, right? And then again we'll calculate the minimum Euclidean distance. So we know dmn will be nothing but SM minus SN, its Euclidean distance taking under root. We know what is SM, it's nothing but Eg by 2 cos 2 pi by m into m minus 1. So I'm not writing the entire thing. This is, we know x1 minus x2 the whole square plus y1 minus y2 the whole square. So this is x1, and what will be x2? Just the index will be n here. So I'm just writing directly because this we already know from our basic school. So 2 by m, it will be n minus 1, and we have to of course take the square, right? So let's just take Eg by 2 outside of the square. Okay, so here won't be under root, so let me just remove it. That under root won't be there in here, right, on this. Okay, but the entire term is having under root. Okay, so just mind it that this is just the first, okay, plus y1 minus y2 is also left, so everything is in under root. So Eg by 2 is again there outside this Eg by 2, okay, in here. And again we can write now the sine terms, because our second coordinate is in terms of sine. So it's sine pi by m and n minus 1 now. And of course we will take the square, and everything is in under root, okay, with plus sign in between. Now we can expand this cosine, that cos square, cos, that is a minus b whole square. So a square minus 2ab plus b square. So this will give cos square in terms of m. This will give by expanding sine square in terms of m, right? And similarly the last term will be giving cos square, and this last term will be giving sine square, both in terms of n. So we will get, we know cos square plus sine square is 1, so we will get 1 from this 2 and 1 from this 2, and both middle term will be there, right? I'm taking new page. Eg by 2 is outside, everything is in under root, I will write it later. We will get 1 for cos square plus sine square in terms of m, and other for n. We will get 1 plus 1, which is nothing but 2, and both are having middle term, that is 2ab, that is 2 cos 2 pi by m into m minus 1 into cos 2 pi by m into n minus 1. And similarly for the second term, the middle term will be in terms of sine, so I'm just writing sine, and everything is in under root, right? Now we know basic trigonometric formulas. We can write this as cos plus cos, so I'm just writing cosine 2 pi by m as it is. First time we will add both the arguments, and for the second time okay, minus sign is outside, we will subtract both the arguments, right? And similarly, minus sign is outside, and we can write 2s as minus cos plus cos. So first will be added, so we are adding the arguments, and second will be subtracted, so it will be subtraction of the argument, and everything is in under root, mind it. Now you can see this term and this term will get cancelled, because minus and minus will result into plus, and plus and minus will cancel this thing, right? So we are just left with this term, and as you can see these are same terms, so twice. So again the new page I'm taking, g by 2 is outside. Now we are having the reduced equation, that twice of cosine 2 pi by m into m minus n, that's it, and this is in under root. So just take 2 outside and we are left with 1 minus cos 2 pi by m into m minus n, that's it. So we reduced our equation in the most compact form, distance between 2 points m and n. And now again, for finding minimum distance, we know that the minimum here will be 1. Mind it that in ASK it was minimum distance 2, right? M minus n minimum was 2, because in ASK we have this amplitude at this side and this side, both side we are having same amplitude. So the maximum, the distance between these two will be 2, right? But here it will be 1, right? So if we'll substitute this as 1, we are just left with Eg and 1 minus cos 2 pi by m, that's it. And you can simplify it furthermore if you want, 1 minus cos theta by 2, so just multiply and divide by 2, and we know this is nothing but sine square, so we can write twice Eg sine square pi by m. Okay, here our theta will be half, so we can take this sine square outside if you want, right? Or you can put it as it is, doesn't matter. But at the end what we want is, we want in terms of EB average, right? So how we'll do this, we know we have already calculated EB average in terms of Eg, right? Let me show you where. So just from where we started, right? So in here you can see where it was, wait, what was the energy? No, this was for the previous. Okay, I'm not able to find it, let me write it again then. Oh yeah, it is. So Eg, since we are having, we started from passband, okay, we are doing everything for passband, so we can write Eg in terms of Eb like this. So from here we can write Eg in terms of Eb, so I'm just writing it. So the D minimum is now given as twice, just writing Eg in terms of Eb log 2 to the base 2, 2 is also there, into Eb average, and sine square is there, pi by m, right? You can take 2 outside because we are having 4 inside, sine square pi by m into EB average. So this is what we want at the end. The minimum distance is this thing, okay, I forgot the under root, yeah, in terms of EB. So you can see that this is the minimum distance equation in terms of EB average in terms of m, right? So that's it about this video. Thank you.